Okay, so now what we are going to look at is how to build a heap. Okay, so this is going to be part of a big picture called, like, given an array of integers like this, we are going to look at an algorithm called heap sort to sort the array. So in order to implement the heap sort algorithm, first we have to build a heap out of this array. So it is a two-stage process. We have to first build a heap and then sort that heap, or make use of the heap to sort the array. So to build a heap, first of all, as we know, there are two conditions, right? So in order to call a binary tree as a heap, it has to be essentially complete binary tree, and then the internal nodes have to have data that is greater than or equal to both the child nodes. Okay, so let us see how to build a heap to satisfy these two conditions. So you will be given just an array like this. So this is an array of 10 elements. Now the first step is to build an essentially complete binary tree. So you all know what an essentially complete binary tree is now. So it should be complete up to the earlier level h-1, and at the last level the nodes are as far to the left as possible. So how to build such a tree from this array? So as I said last class, we just look at the heap as an array means we are going to traverse the heap in top down, left to right fashion. So at the root level, which is level 0, we are going to have the root node, which is node at index 0 and its corresponding data phi, and the next two levels we are going to so next level you're going to have the two child nodes at index 1 and 2. Then so top down, left to right. So now after this level, the next level, left to right. So we are at index 2, so this should be index 3 and 4 for node 1. Then for node 2, index 5 and 6. Done with this level. The next level, left to right. So for this, we are until 6 here, so this should be 7 and 8 for node 3. Then for node 4, the last index data 9. Okay. So again, we can remember we saw a property that for any internal node at index j, its two child nodes are at index 2j plus 1 and 2j plus 2, and that is implicitly satisfied here. So if j is 0, 2j plus 1 is 1, 2j plus 2 is 2. If j is 3, 2j plus 1 is 7, 2j plus 2 is 8. If j is 4, 2j plus 1 is 9, and 2j plus 2 is 10, but 10 is out of the range. So the array has index only up to 0 to 9. So when you get a child index that is outside the range, that means that node is missing that child node. Okay, so by arranging the nodes in top down, left to right fashion, we can get an essentially complete binary tree. Again, as I indicate here, this is not a heap yet, because in order to call it as a heap, it has to either satisfy the max heap or min heap property. So we are going to work it as a max heap for all the for all the algorithms in this course, but I could ask you to do something with a min heap. So the only thing you have to remember is for a min heap, for any internal node, its data is going to be less than or equal to the two child nodes. So that's the only difference. So all algorithms you're going to see for a max heap are also applicable for a min heap. Okay. Alright, so how to convert this essentially complete binary tree to a max heap? So that's what we're going to see now. Alright, so we are going to go through a sequence of iterations. So this is called the Heapify process. Now again, as I said, you can do all these things with just an array. So once you build an essentially complete binary tree, we can work with the array itself. Okay, so all the changes I show here in the binary tree are just for visualization. So if you're really coding this, you could do this with an array itself. Okay. Alright, so this is the array that we are given, that's the input array. So now we're going to go through a sequence of iterations to re-heapify and kind of convert this essentially complete binary tree to a max heap. So again, what is the max heap property? We have to check only for every internal node, its data has to be greater than or equal to the two child nodes. So the internal nodes, if you remember, are going to be in what range? So once you say it is an essentially complete binary tree, if you remember this, the internal nodes are going to be range 0 to n over 2 minus 1, and the child leaf nodes are going to be from n over 2 to n minus 1. So in this case, for example here, the internal nodes are going to be, so this is an array of 10 integers, so n is 10, so n over 2 is 5 minus 1, so 4. So the internal nodes are going to be from index 0 to 4, and that's what you see here. That's this node at index 4 is the last internal node, and everything from n over 2, which is 5, to n minus 1, which is 9, are all leaf nodes. They don't have any child node. Okay, so we start this process from the last internal node, okay, which is node 4, index 4 here. So we'll check its data with its child node. So the data of the internal node is 3 and its child node data is 8. So that is not satisfying the max heap property. The data for internal node should be greater than or equal to the data of the child nodes, whereas here 3 is less than 8. So what we have to do is we have to do a swap. So 8 comes here, 3 comes here. So we can do that with an array itself, because we know the internal nodes are going to be from 0 to index n over 2 minus 1, which is index 4 here. So we start with index 4 and check the data of its two child nodes. So for index 4, the child node will be at what? 2 times 4 plus 1, 9, and 10. And of course 10 is outside the range, so that means this node at index 4 has only a left child at index 9. So compare the data 3 with 8. 3 is less than 8, so we need to swap. So 8 comes here at index 4, 3 goes here at index 9. So that's what we do with an array. So now this is the updated binary tree and the array here. So now we repeat the same process at all internal nodes. So the next previous internal node is at index 3. Now check its data, which is 4, with the data of its two child nodes at index 2j plus 1 and 2j plus 2, which are 7 and 8. So you see here 4 is not greater than or equal to both. There's at least one of the two child nodes having larger data. So if that is the case, what we have to do is we have to find which child node has a larger data, and then swap the data of the internal node with that child node. So we swap 7 with 4. So 4 comes down, 7 goes here. So that is, we have to do the corresponding change in the array also. So in an exam, if I ask you to show the stages of the iterations, you have to draw both the binary tree version as well as show the update in the array also. Okay, so now we're looking at internal node 2. So it's two child nodes, so the data is 5 and the child node data are 10 and 7. Both are larger than the internal parent node. So we have to find the larger of the two child node data, which is 10, and then swap 10 with 5. So 10 comes here, 5 goes down here. So then node at index 1, you see here it is 6 and this is 7 and 8. So the larger is 8. So we swap 8 with 6. Now when you swap here, you see here this position that we have reached is not a leaf node. Until now, in the previous iterations, if you notice what happened, we do a swap here. So this child node is a leaf node. So there's no further node further down. So we don't have to check if, because of the swap, the max heap property is changing here or not, because this is a leaf node, it's not having a child node. Again, this is a leaf node, so after we do the swap, we don't have to check if the max heap property is changing further down. Again, the next iteration, this is a leaf node, so after swapping 5 comes here, we don't need to see anything further down is going to be affected because of this. But you see here, now if you swap because of this internal node, 6 is less than both its child nodes, so we swap with the larger of the two child node data, which is 8 with 6. 6 comes down here. Now we have to check is because of that whether this node's, it means the index 4, this node's child node is going to be affected or not. In this case, if 6 is here as the data, it's fine to have 3 as the data of the child node because 6 is greater than 3. If you have something that is less than, if you have something that is greater than 6, so this is 6 here now, so if we have say 7 or something, we have to swap again, and we'll see some positional cases like that. Okay, so let us see here. So so we did internal node 1 index 1, so now we have to do index 0. So when we do that, you see, first check the data, compare the data of the internal node, which is 5, which is 2 child node data, both are larger, so find the larger of the 2 child nodes, which is at index 2. So swap 10 with 5, so 10 comes here, 5 goes here. Now because of that swap, this node is now having data 5, so you have to check if the data of this node is now larger than or equal to both its child nodes. So 5 compared with 5 and 7 is not, so we have to now again find the larger of the 2 child nodes and swap them. So 5 is swapped with 7, so 7 comes here, 5 comes down here. So that's what you have to check. So if you happen to swap the data down to an internal node, we have to check further down. Okay, so we went through the iterations from index 4 to all the way to index 0. So after we done with index 0, what we have is a max heap, because what we just made sure for every internal node, its data should be greater than or equal to its child nodes. So that's what we have done here. Okay, so if you look at the time complexity of this algorithm of reheapifying an essentially complete binary tree and converting that to a max heap, we do how many iterations? We have an array of n elements. We start from n over 2 minus 1 and go back to index 0, so that is approximately half the size of the array. So we do n over 2 iterations, and for each iteration what we do is we do a swap. We could do one swap, or like in the last case here, we could do more than one swap. So at the worst case, how many swap operations we have to do per iteration? So if you look at say the root node, we did 2 swap operations here, and it could be that this node has a child node further down and we may have to do a swap also. So the maximum number of swap operations we do per iteration corresponds to actually the height of the binary tree. So we could do some the reheapify operation at the node at index 0, and we have to swap all the way further down to the last level. So that's the maximum number of, or worst case number of swap operations. So for a binary tree of n nodes, the height is going to be log n. So the max number of swap operations we'll do is log n number of swap operations per iteration, and we have n over 2 iterations, so n over 2 times log n, so that's like n log n. So that is, again, it's big O of n log n, because we have here the worst case we have to do what is called log n time number of swap operations, right? So at the minimum we can do just one swap operation per iteration, whereas the worst case we have to do log n operations, or log n number of swap operations. So that's why the time complexity of this algorithm of transforming essentially complete binary tree to a max heap is big O of n log n time complexity. Okay, so now let us look at the code for this. So the first part of the code, so is the main function. So we are just setting up the array of random integers. So you all know how to do this now. So get the array size as input, get the max value of the array as also as input, then set up the random number generator and go through a loop to fill up the array, right? So now so the array index is from 0 to array size minus 1. So we're assuming that it is treated like that, from 0 to array size minus 1, and index 0 to array size over 2 minus 1, that is n over 2 minus 1. So n is the array size, so array size over 2 minus 1, that is the index of the last internal node, n over 2 minus 1. So we are going to assume that this array is an essentially complete binary tree, because we're going to process from index n over 2 minus 1 to index 0 as internal nodes, and everything further from array size over 2 to array size minus 1, that is n over 2 to n minus 1, are all leaf nodes. Okay, so as we just did, we are going to do the iterations to reheapify. So we are going to start the iteration from index n over 2 minus 1, that is array size over 2 minus 1, and call this function rearrange heap array. So that is the function to do what's called this reheapify, and you're passing 3 arguments: the array pointer, the size of the array, and the index where we want to do this reheapify. So here we are doing the reheapify at index n over 2 minus 1 to begin with, and then progressing all the way to index 0. So that means you have now look at the code for this rearrange heap array. This is the code for that. So if you remember what we just did in that example, once we get to that index, so this is the array pointer, the array size, and the index where you want to reheapify, we find the index of the left child and right child. So that is simple. If you know index is j, then left child id is 2j plus 1 and right child id is 2j plus 2. So that's what I show here. So 2 times index plus 1 is the index for the left child, and 2 times index plus 2 is the index for the right child. So now we have to check whether the left child exists, and then if it exists, we have to compare the data. Similarly, if the right child exists, we have to check the data. So first we have to check for the left child. So how we check the left child exists? So if left child index is greater than or equal to array size, so this is like, as I said here, if you're looking at index 4, 2j plus 1 is 9, but 2j plus 2 is 10. So if you get a child index that is greater than the last valid index, which is 9 here. So in this case we have 10, which is greater than or equal to the array size. The array size is 10, so array size is not a valid index. Array size minus 1 is the last valid index, because indexing starts from 0. Array size minus 1 is the last valid index. So if you get the index to be array size or larger, okay, so for example, if this is our index j, 2j plus 1 is going to be 11, that is going to be larger than the array size 10. So if it is greater than or equal to the array size, if the child index is greater than or equal to array size, that means that node doesn't have that child. So in this case, you're checking if the left child index is greater than or equal to array size. That means that node at that specific index does not have a left child. Again, remember, we are assuming that the binary tree is essentially complete, and we now find out that node that we're currently looking at is not having a left child, and since it is essentially complete, it's not going to have a right child also. So we can just return from this function right here for this reheapify array at this index. We don't need to really reheapify if the node doesn't have a left child. So if the control happens to go further down, that means the node does have a left child. So now we are going to check whether the node has a right child. So if the right child index is greater than or equal to array size, that means the right child index is an invalid index, is greater than or equal to array size. That means the node has only a left child, because as I said, if the control goes further down, left child index is not greater than or equal to array size, it is less than array size. So that's why we are able to go further. But now if right child index is greater than or equal to array size, that means right child does not exist. So if you happen to get inside this if block, if right child index greater than or equal to array size, that means that node has only a left child and no right child. So that means we have to compare the data of the node at this index only with the data at left child index. Okay, so that is like this node 4, it has a left child index which is 9, a valid index, but the right child index is 10, which is not a valid index. So this node at index 4 has only a left child. So all we have to then do is compare the data of that node with the data of its left child and check if it's fine. So like here we compare array of index with array of left child index. So here we have less than. So if the data of the internal node at index is less than the data of its left child, like in this case, in this case 6 is actually greater than 3, it's fine. Or you're looking at the final heap, right? Let us go here. like here. So 3 is less than 8. So this is not acceptable for a max heap. Then what we do? We did a swap, right? So that's what we have in the code here. So if the data of the node at index is less than the data of its left child, then we have to do a swap. And this is the regular code that we always use for swap. Use a temporary variable, assign the data of one of the two array elements to that temporary variable, and then do the swap. Okay. So that means now what did we do so far? The node has a left child but no right child, and we compare the data of the node at index with its left child data, and we did the swap if needed. We're done. So we can return from this function for the Heapify at that index. Now if the control goes further down, that means what? We did not get inside the this if statement, because if we get inside this if statement where right child is greater than equal to array size, we would have returned from here. So if the control goes further down to this code, that means what? That means the right child index was less than array size, right? So again, left child index was less than array size, right child index is also less than array size. That's why the control was able to come this point. So that means the node has at that index has both a left child as well as a right child. So now we have to check the data with both the nodes. So array of index is greater than or equal to array of left child index, and array of index is greater than or equal to array of right child index. That means if you are checking if the data of the node at index is greater than or equal to the data of its left child as well as the data of its right child, that is fine, because that's what we want for a max heap. So we simply return from this function. So if you go further down, that means this condition is not satisfied. Again, remember, so we reach until this point if the node has both the left child and right child, and this condition is not satisfied. That means the data of the node at index is less than at least one of its two child nodes. So now we have to find which of the two child nodes has the larger data. So I start with assigning, say, the left child index as means the left child is assumed to have the larger data. We are going to check that. So I say make use of a temporary variable called max index and set that to left child index. Then comparing the left child index with the right child index, the data. So if the data at the left child index is less than the data at the right child index, that means the right child has the larger of the two child node data. So I set my max index to right child index. So if the data as the left child index is greater than or equal to the data of the right child index, so max index will continue to stay as left child index. So this is the place where you can decide about breaking the tie. So if both the child nodes have the same data, okay, so which one is considered to have the maximum larger data? Will say the left child has the maximum data, okay, because you see here the max index is set to left child index. So the max index will be set to the right child index only if the right child has really larger data than the left child. Otherwise, the left child is considered to have the maximum data. So then once we decide which of the two child nodes has the larger data, that is captured in the max index. So it could be either left child index or right child index. Then we swap the data of that max index with the data of the node at index. So we set them variable is array of max index and swap that with the node at index. So now we are not done yet, because we did the swap of an internal node with data of its child node, right? So because of that, the max heap property could be affected further down. So let us go to this scenario here. So we kind of say index is 0 and max index this case would have been 2, right? Because index 2 data is 10 and index 1 data is 8. So the right child index has the larger data. So max index is 2. So we did the swap with index 0 and max index is 2, and 5 comes here, 10 goes here. So because of this, the max heap property could be affected further down. So we have to really re-heapify at index 2. which is max index. So that's what we're going to do here. Call the reheapify function, the rearrange heap array function, recursively. Array size, so the three arguments, right? So array size. So this original rearrange heap array function was called at index, which is index 0 in that example. So now we have to call at max index, which is index 2. So we start with the earlier with the top level and then go further down. And then since you're calling this recursively, it will automatically take care of if you go through all this process and we have to again reheapify further down, this the way we have set up the recursion will take care of it. Okay, so I'll give you this code. I did not post yet it in Canvas. I'll post it after the class today. So you have to build on top of the code for your assignments. So you have to understand this C++ code in order to do some of the assignments. Okay, stop here for a second and do a record my video.